So this talk is, as you probably guessed, about emergent design, and this is a part of the really interesting piece of the kind of agile architecture world, because this is about architecture and design. I've actually written quite a lot about this subject, and there is an article series out there on IBM Developer Works. There are 19 installments in this series on evolutionary architecture and emergent design, and I'll explain where that name comes from in just a second. That's a hideous, awful URL, so you don't want to use that. This is a much friendlier, modernized, shortened version of that, but this has a link to Developer Works and has some of the stuff I'm talking about here and lots more stuff out there as well. What I'm going to be talking about in this particular talk, my agenda, is to poke around a little bit and investigate what we mean when we say software design. And I want to tease apart the distinction between architecture and design, because if you can separate those things, you can build separate techniques around each one of them. I'm going to talk about things that make emergent design difficult. Then I'm going to talk about some things that make it easier and enable it. And then finally, I'm going to talk about some concrete techniques for once you discover these little patterns lurking in your code to help you find those things and then harvest them and take advantage of them. But I'm going to start with the poetry of Donald Rumsfeld, who very famously said, "There are known unknowns." That is to say, there are things that we now know we don't know, but there are also unknown unknowns. There are things we do not know that we don't know. And he didn't realize it at the time, but he was really talking about software when he said this, because this, it turns out, is the killer characteristic of software. It's the unknown unknowns. Because you go into projects with some known unknowns. We need to add geocoding to this application, and I'm not quite sure I can spell geocoding, but you know that you need to reserve a chunk of time to investigate and learn how to do geocoding. You can anticipate that as the unknown unknowns that is the killers. And that's the real nail in the coffin to all the big design upfront kind of techniques and softwares. They all suffer from the unknown unknowns and end up nabbing them in the end. So there's a lot of effort in the agile architecture world to try to stop reacting to things that we don't know and instead build emergent and evolutionary style architectures and designs. Because we realize at some point the future is really, really hard to predict. And instead of trying to build a better and better crystal ball, why don't we step back from that and make the future when it comes not quite so scary? So one of the questions that I want to answer, or at least start to answer in this talk, is this one. What do we mean when we say software design? And fortunately, someone has already answered this question for us. In an essay written in the fall of 1992 in the C++ journal, Jack Rees wrote this very famous essay called "What is Software Design?" It's still available there, and it's still well worth reading because you would think that it was written yesterday. And one of the interesting things Jack Rees does is try to do a deep metaphorical comparison between traditional engineering and software engineering, as opposed to the very shallow metaphorical comparison that we use when we describe what we do to our parents or our grandparents. Yeah, software development's like bridge building. No, it's like gardening. No, it's like mountain climbing. These are all very shallow metaphors. He tried to do a deep metaphorical comparison between traditional engineering and software engineering and reach some interesting conclusions. One of which is the final goal of any engineering activity is some type of documentation. If you're a civil engineer and you're tasked with designing a new bridge, what is your output for that task? Is it a new bridge somewhere? No, it's a plan for a new bridge with very specific environmental constraints in place and with the due diligence in place to understand what stresses and other sorts of characteristics need to go into that bridge. When the design effort is complete, that design document is turned over to a manufacturing team, which is a bunch of guys who know how to take architectural plans for bridges and actually pour concrete and rebar and make it into a real bridge. But now we get to places where there's a deep difference between traditional engineering and software engineering, because manufacturing for physical things means stamping out atoms into new shapes. And it turns out it's hard to refactor atoms. Once you've got them stamped in a particular shape, doing something beyond just melting them down and restamping them is very difficult. And so in the traditional design world, when you had hard constraints over the things you produced, there was a lot of need to do a lot of design up front because the manufacturing process was very error-prone and had to be very precise. But we don't deal with atoms in our world. We deal with bits, and bits are very, very soft. In fact, it's called software for a reason. So what is the manufacturing process for us? What is the thing that takes a design and converts it into something that manifests in the real world? It's compilation and deployment. That's our manufacturing process. What that suggests is that in our world, our design document, our blueprint from an engineering standpoint is the source code. And not just some of it, the complete source code. Because any change you make to this document changes what gets manufactured. So even if a QA person suggests a bug, that bug means you change something in the source code which changes the thing that gets manufactured. But here's another big difference between traditional engineering and software engineering is that traditional manufacturing is expensive. Stamping out atoms is expensive. The reason that they developed all these techniques for civil engineering was not particularly to make safer bridges at first. It was a cost-saving measure because it's simply too expensive to build prototype bridges and roll heavy stuff over them to see if they collapse or not. So they needed to invent all this predictive kind of math because it's really expensive. But software is not expensive at all. In fact, every time you stop typing, an army of gnomes inside your computer springs to life and manufactures your design on the fly for you. You don't even think about that happening anymore because compilation is just this magical background process that just happens. And so Jack Rees says, given that software designs are relatively easy to turn out and essentially free to build, an unsurprising revelation is that software designs tend to be incredibly large and complex. The last part of that quote got cut off, but the last part of it is that they tend to be incredibly large and complex. We just think that we're bad at software design. It turns out it's a fundamentally hard problem to solve. It's one of the hardest problems that we try to solve from an engineering standpoint. And here are a couple of reasons why. Here is a US-based plug, but just imagine if this were a much larger UK-based plug. And imagine it were part of this hotel on the wall over here. And you'll notice over here that the case doesn't quite cover the hole in the wall. A similarly small error in a piece of software will cause that software to crash and fail, but that small problem will not cause this building to collapse if that happens to be the case. So the tolerances in software are impossibly fine compared to the real world. One small thing will make your software stop functioning. Now, it's easy to spackle in that hole and just remanufacture the whole software stack, but the tolerances are really, really fine. We also don't have locality of fault to origin of fault. We may have a condition that sets up an instability that doesn't manifest for 100,000 lines of code away. If you're an airplane forensic engineer and the wing falls off an airplane, your first place is probably go check where the wing is connected to the airplane because there's a locality of fault to the cause of the fault, which we frequently don't have in software. We also don't have the same kind of economy of scale. The Golden Gate Bridge in San Francisco has more than 1 million rivets in it, and you can bet that the people who understand the structural characteristics of bridges can tell you what contribution those million rivets make to the overall structural integrity of the Golden Gate Bridge. We build things that consist of lots of parts too, but every one of our parts are handcrafted. This is back like when blacksmith used to make nails. You know, that was the blacksmith's #1 job, not making horseshoes, but making nails, because people needed nails to build houses, and each one of them was unique because they were handcrafted nails. That's exactly how we build our tools and software now. All of them are handcrafted. It has defied our ability to create reasonable components in software, although we keep trying, we're at the wrong level of granularity. Traditional engineering has spent a few thousand years working on mathematical techniques that give them predictability, so they don't have to build bridges to test them to see if they're going to stand up or not. And for quite a long time, big companies like IBM tried to do the same thing for software. Back in the 60s and 70s, IBM got disgusted at how wishy-washy this whole software engineering thing was, and they sent Fred Brooks and Barry Boehm off and said, make this a real engineering discipline. And mostly what those two guys did when they got finished was write books about how this is never going to be a real engineering discipline. That's where Mythical Man Month and all that research comes from IBM. But it turns out that this is probably chasing something we don't need. Because the reason they have all this predictability in engineering is because it's so expensive to build stuff. But our manufacturing is essentially free. I mean, every time we stop typing, we get stuff manufactured, and so we can easily manufacture things in realistic kind of environments and test the real thing and not the predicted behavior of the real thing. So for us, we get engineering rigor in testing. Believe me, architects would love to be able to take a small subsection of a building and see what kind of stress it reacts under in a realistic way, and while they have some tools to do that, it's still predictive around math, it's not the actual thing. And I also think that if architects could actually do test-driven development, we would have the most elaborate Jetsons-like buildings you've ever seen in your entire life. Testing is the thing that gives us confidence that even though we have this pile of disparate parts, we can separate each one from the pile and completely understand its characteristics before it goes back into the pile and contributes to the larger piece of our software. And so Jack Reeves concludes his essay by saying software may be cheap to build, but it is incredibly expensive to design. Because basically, everything that you do in software that might change the source code is part of the design process. So that means that testing is part of design, QA is part of design, operations is part of design, because if your operations group comes back and says you can't use this piece of library from the internet because of a security concern, that's changing your source code, that's part of design. And this is a really, really expensive thing, and so part of the idea in emergent design is let's try not to waste a lot of this really, really expensive design time. So I talked about this distinction between architecture and design. There was an essay that Martin Fowler wrote a few years ago, probably 5 or 6 years ago, called Who Needs an Architect? And it's still on his website. And he's talking about the role of architects in agile projects. And he sort of accidentally gives what is still my favorite definition of the architectural elements in software, where he says that the architectural elements in software are the things that are going to be hard to change later. And so for any piece of your software stack, you can kind of ask it, are you going to be hard to change later? And that determines if it's an architectural element or a design element. So for example, the database you use is architectural because you can't easily change that out. The web framework you use is architectural because you can't easily change it out. But the way you use that web framework, the way you use its validation bits and how you use its workflow, those are all aspects of design, which are things that are relatively easy to change later. And this very abstract blocks diagram is trying to capture the sort of essence of this in that these gray boxes at the bottom represent architecture. And you can't have software without architecture. There's no such thing as emergent architecture because the architecture is the thing everything else rests upon. That's why I make this distinction between evolutionary architecture and emergent design. Because the cost of change is less expensive for design elements, you can afford to let those emerge over time. But for the architectural elements, something has to be in place. And so part of our effort there is to make it so you can evolve those architectural elements slowly over time and make as many things as you can cheaper to change by making them design elements. Because the other half of this definition is you really want as few architectural elements as you can get away with. Because while architectural elements provide scaffolding and code you don't have to write, it also represents constraints that you're introducing. And what you want in the perfect world is all the capabilities and none of the constraints, and you try to optimize toward that. Most of this talk, I'm going to focus on the top part of this, the red boxes here, around design, and in particular, this idea of emergent design. So I should give a definition. The Webster Dictionary says that something that is emergent if it rises out of something that covers or conceals it or comes to light. And a second definition says something suddenly arising or suddenly appearing, arising unexpectedly, and calling for prompt action. These two definitions loosely correlate to the two different aspects of emergent design I want to talk about. And here's the first one. Let's say that conceptually you have a problem that's like this. It's kind of a tangled mess, and there's relationship things between things, but you can't quite discern what that relationship is. And you think about this while you're at work, you think about it while you're riding the tube on the way home, and you think about it when you're mowing your yard, and when your spouse is talking to you and you're supposed to be paying attention to them. There's still a background thread that's kind of thinking about this problem at work and trying to figure it out until you finally think about it enough until it resolves itself in some sort of reasonable, meaningful structure. That's this exercise of finding abstractions and patterns that already exist in your code. You just need the ability to go find them and harvest them out of your code. So this is very much an existing project kind of emergent design technique, or a brownfield project kind of technique where you're looking for things in existing code. And I'll show you, using some metrics and other things in just a minute, of some techniques where you can go find hidden little design things in your code. But when we talk about patterns, I'm not talking here about the formal Gang of Four design patterns, which are patterns with a capital P. I'm talking about patterns with a lowercase p and what I'm calling idiomatic patterns. I maintain that every piece of software has idiomatic patterns down inside it, and I further subdivide these into technical and domain idiomatic patterns. Things like validation, security, and transactional boundaries are all things like technical idiomatic patterns. Things like business rules and shared functionality are all domain idiomatic patterns. But used in this way, when we say patterns, we're really describing effective abstractions. I've solved this particular problem, and I'd like to leverage the solution the next time we encounter this problem. Not formal enough to write a book about. So for example, the way that your company handles authentication and authorization is probably a big deal for your company, and there's a lot of details on how you do that. It's not exactly like any other company. In fact, no other company cares about how you do that, but you'd like consistency across that, the way that happens in all your applications. That's a technical idiomatic pattern within your organization. So one half of this idea of emergent design is going and finding and harvesting those idiomatic patterns that already live in your code. The other aspect that loosely correlates to the other definition from Webster is this concept from the lean manufacturing world of the last responsible moment to make decisions about things. And the idea here is that every time you're asked to make an important decision on a software project, ask yourself a question: can I safely defer this decision until later? Because one of the tricky things that we are often required to do on software projects is make the most important, nuanced decisions about that project at exactly the time when you are least qualified to make that kind of decision, which is before you started working on the project. Very often, architectural constraints come in very early on because they're hard to change later, and if you do that without having a lot of knowledge, then you end up building yourself kind of a quagmire. The idea behind the last responsible moment is if you can safely put that decision off a little time, you will start building real knowledge and context for this project and not some other generic kind of project. And so the potential is better if you can wait longer, but of course you don't want to wait too long because then you're actually causing yourself more headaches than necessary. And this is one of the truly tricky things in the agile architecture world, is exactly how do you identify this last responsible moment. I'll give you some pointers and a case study for a project that I think nail this in just a moment. And I want to talk about things that make emergent design possible, but first I want to spend a couple of minutes and talk about what is unfortunately way more common in most of our worlds, which are things that make emergent design hard. And the first of these is the nature of complexity in software. This was first really elucidated by Fred Brooks and some guys like that. But it turns out that software has two kinds of complexity. There is essential complexity, which is the inherent complexity of the problem you're trying to solve. Some problems are more complicated than others. A bubble sort is less complicated than a quick sort, so there's fundamental complication in those things. But we also in software deal with a lot of accidental complexity, which is all the truly innovative ways we have figured out to make software more difficult to understand. I think that's where the real innovation is happening in software, is obfuscating what we're trying to get done. But a lot of emergent design is understanding what's essential versus what's accidental, because obviously you don't want accidental complexity in your software. And there are examples of this, because this is a spectrum. It's not just a binary proposition. And there's some famous examples of this. The first famous example of this was hunting season. In the original Extreme Programming project, it was a human resources project for an auto manufacturer that had facilities in multiple cities, multiple states. And one of the union representatives for one of the auto manufacturing facilities had a special clause built into their contract that said all their employees got the first day of hunting season off as a paid holiday. It's a really clever union guy. But the XP guys were tasked with writing this HR application, and it turns out that made their code way more complicated, because every time you calculate number of days, there's a special case for this one facility. And the developers on that project would have loved to go on to the business guy and said, you know what, that whole hunting season thing sounds like a good idea, but yeah, you can't have that because it's making our software too complicated. We don't have that option, so we just have to figure out an elegant way to handle that. That is the essential complexity of the problem. But then you get into situations where you start imposing complexity where it doesn't really need to be there. Things like field level or really fine-grained security on a page or a form. I've seen this request manifest a lot of times. You say, okay, we can build that. So you build all this elaborate infrastructure, this really fine-grained security, and then you build a way to administer all this fine-grained security. You roll it out to your users and say, ta-da, there it is. And they go, wow, this is really hard. I don't have to do this for every page. Which surprises me that there's not more workplace rage in the software world, because you've poured your heart into this beautiful, elegant design and your users kind of turn their nose up at it. It turns out, though, that one of the problems we have in software is that users often request things that they've never actually seen, they've only fantasized about, and sometimes your fantasy life is richer than your real life. So when it really comes to life, it's nowhere near as cool as you thought it was going to be. Which is one of the big reasons in the Agile world we say get it in front of users as quickly as possible so that it's not the fantasy Antonio Banderas version of the combo box. It's a more realistic kind of working man's combo box. And then you creep a little further along the spectrum and you end up with things like Enterprise Java Beans and BizTalk. Which is not to say those are fundamentally flawed technologies, but they're so often applied inappropriately. Because these are these big, gigantic architectural frameworks. And so the question comes up, are we ever going to need declarative distributed transactions on this project? And it's like, well, if this project exists for a decade, maybe we will. It's like, okay, let's put the EJBs in now. Of course, dooming this project to never, ever make it to a decade's worth of use, because you'll never get the thing out the door because it has too much accidental complexity from the outset. Part of the trick in emergent design is looking at accidental complexity and realizing it for what it is. The second thing that makes emergent design really hard is encroaching and ever-increasing technical debt on projects. This is a metaphor that Ward Cunningham came up with. It's another kind of nice, deep metaphor in software. Everybody here knows the gut feel for technical debt. It is the delta between good, clean, perfect design where you lavish all your love and attention on a design and no refactoring is too large or too small to make it this perfect, pristine thing, versus what you left to come here today. The delta between those two things is technical debt. And several things drive technical debt. In fact, Martin Fowler, our chief scientist, has created a quadrant of things that get you into technical debt. And he has labeled these as reckless and prudent and deliberate and inadvertent. And so in the reckless and deliberate category, it's that we don't have time for design. You get busy working on it, and I'll go see what they want. The prudent and deliberate is we have to ship now and deal with consequences. This is also known as schedule pressure, which is a huge driver for technical debt on many projects. The reckless and inadvertent is what's layering? This is I love putting all my code in a single JSP or ASP.NET page so you can just scroll up and down and see all the global variables that you need to access. And then finally, prudent and inadvertent, now we know how we should have done it. Hindsight is 20/20. In fact, one of the interesting pieces of advice that Fred Brooks gave in Mythical Man Month is if you want a really well-designed piece of software, write it one time and then throw that one away and then write it a second time, and the second one will be awesome. You know what else about the second one? You can estimate that thing to the day as to when it's going to be done. You know why? Because all the unknown unknowns have been resolved. Once you've built it once, there are no unknowns left. And so you can build a proper design taking all those things into account. If you do it a second time, it is unfortunately a slightly expensive way to design software by throwing the first one away every time. The real problem with technical debt is not its existence, because just like regular debt is not inherently a bad thing. The problem is, as developers, we're really terrible at negotiating repayment. And this is the real skill that we need to hone, not dodging technical debt, but getting payment. Wouldn't you love to live in this world where your boss comes to you and says, we need these 3 new features, and you say, nope, I'm sorry, you've reached your credit limit on technical debt on this project. If you'd like to speak to one of our representatives, we might get you a temporary extension and get you a few features, but if you keep abusing this privilege, we're going to declare technical debt bankruptcy on you and never listen to you again. Wouldn't that be an awesome world to live in? Unfortunately, we don't live in that world. So what you have to do is convince someone that technical debt exists before you can ever start a conversation about repayment. And this, we have reached my favorite mantra in the agile engineering world. And this works here and it works in a lot of different places, and that is demonstration trumps discussion. Stop talking about it, demonstrate it. It's hard to argue against objective results, and you can argue about people with subjective things until the cows come home. So, how do you demonstrate technical debt? Let me show you a few techniques. First, we need a metric. Many of you are familiar with this metric. It's been around for 1,000,000 years, since the 1970s. Cyclomatic complexity, also known as McCabe's complexity. Thomas McCabe created this. The idea of cyclomatic complexity is to assign a numeric value to the complexity of a method or a function. Here's the formula: edges minus nodes plus 2, where nodes are lines of code and edges are possible pathways through that code. So if you look at a little max method that looks like this, you can sketch it out in its edges and nodes view, and 4 minus 4 plus 2, so the cyclomatic complexity of this code is 2. It's kind of boring when the edges and nodes cancel each other out, so here's a slightly more complicated function. You draw out this edges and nodes view and label them. 8 minus 7 plus 2, so the cyclomatic complexity of this guy is 3, so this is one more complicated than what we saw before, the function we saw before. This is a really useful metric in lots of different ways. One of the fun things to do with this metric is take this home and run it against your code base. You can find easy metrics tools that do cyclomatic complexity, and go look at the top 5 most complex methods in your code base. Then ask yourself this question: is most of that complexity essential, or is it accidental? If you look at those top 5 methods and answer that question, there's a pretty good indicator of the overall quality of the code base. At least it seems to correlate that pretty nicely. The other cool metric that's available with cyclomatic complexity is that there is a rough correlation between cyclomatic complexity and too much accidental complexity. Let me show you a visualization for this. This is a graph that was created by one of my colleagues, Eric Dernenberg, who's done a lot of interesting stuff in the software visualization space. This is from a real software project, from a snapshot from April 1st, 2006 to August 18th, 2007. This is a public-facing media site, and the red line there is cyclomatic complexity per line of code, and the gray numbers that are overlaid it are the releases of this software. Just by looking at this graph, what do you think the first public go-live release for this piece of software was? The 2 common guesses are 3 and 7. 3 is actually the correct answer here. What you're looking at with all this churn is really just a manifestation of technical debt. We're hacking stuff into the code base and then hacking some complexity out. And that churn is very characteristic of a lot of encroaching technical debt, because there's a lot of churn going on. When they hit their public release, Eric produced this much of the graph and took it to the powers that be and said, okay, look, we made our date, but we've incurred some technical debt along the way that we need to service. Now, what if he had not produced that graph and had just ignored that phenomenon and then just kept charging forward full steam ahead? What would happen in this graph was it would keep rising in this spiky kind of manner, and the overall effect on your project is that everybody's velocity gets a little slower and slower and slower. Because what happens when you have a lot of technical debt in your code base, it's very much like growing a garden and letting weeds start growing. If you let the weeds grow to a certain point, you can't see the vegetables anymore. And when it comes time to harvest the vegetables, you have to sort through a lot of weeds before you find the vegetable that you're supposed to do something with. And code base is the same way. When you build up more and more technical debt, the legitimate changes you need to make to it become harder and harder and harder over time because there's so many compromises in the code base. So he convinced them that that was the case, and so the release 3.0 and 3.1 were refactoring releases that were just doing technical refactorings, and you can see that the complexity calmed down significantly and kind of bottomed out there around release number 7. It started creeping up again in a much more controlled way because they actually changed the project structure and started doing more integration, broke it into a more services architecture and started integrating the two. And there's a little bit more complexity in terms of integration architecture, and you're seeing that reflected in the complexity, but a lot less volatility than we saw before. So this is a good example of fine ways to demonstrate things like technical debt because they're much harder to argue against. There are a lot of really nice tools out in the world that will assist you in doing this. There's some really nice tools in the Java space in particular. There's an open source tool called Sonar that gives you a bunch of nice visualizations for some common metrics. They run a sample instance that shows a bunch of open source projects running under Sonar. And the reason I bring this up here in this section is they have a technical debt calculator built into Sonar. What it does is look at some of the characteristics of your code base, like how much code coverage you have, how many duplications do you have in your code base. That's another illustrative tool to run on your code base is the copy and paste detector on your code base and see how many people have been copying and pasting code. Cyclomatic complexity, et cetera. So you can actually run this and then present this as, here's our sum technical debt. Fair warning though, in my opinion, this tool produces numbers that are on the high side. This is for struts, and it's claiming it's going to take $250,000 to make struts so it doesn't suck anymore. I don't think that's true. So if you just take this and run it against your code at work, and it comes back and says it's going to take £2.5 million to make your code not suck anymore, and you take it to your project manager and show it to him, and he's going to jump out a window, I don't be responsible for that. So you need to modify these numbers a little bit. What you want to do is scare them enough into action, but not terrify them into like suicidal impulse. So it's up to you to find that range of where you want to talk about technical debt, but you're going to have to find that because I'm not responsible. The other cool thing that Sonar has is a lot of really nice visualizations in terms of graphs. So if you have a boss that has such a bad attention span, they have a hard time understanding words anymore. You can start showing them pretty pictures with colors on them. And if they're so far gone they can't really understand that, so this is what you want to see, is a nice ascending complexity over time, but really nice flat code coverage and complexity per method. If your boss is so far gone they can't even look at pretty pictures anymore, Sonar will actually give you Gapminder and starred visualizations. This is complexity over complexity per method in the struts code base, and you'll see that something horrible happened to struts around the 1st of September in 2009 when they merged another code base into the struts code base, and the little bouncing ball sprinted to the upper right-hand corner because he's now embarrassed at how complex his code base has become. This is a nice kind of visualization to have in case you merge with a truly dysfunctional company from an IT standpoint, and a year later somebody says, why is everything a wreck around here? You can say, ooh, I have the answer to that question. I can show you when it happened, the day it happened. So it's nice having some forensic metrics like that. The third thing that makes emergent design really difficult is rampant genericness. We have this attitude often architecturally that we want to build lots of layers for extension so we can easily build more into it later, the supposition being that all those extension layers are free, but very often they're not. The problem with this is it increases the complexity of software. Entropy is a mathematical measure of complexity, and if you're adding new features into your code that you know that you don't need yet, then you have or adding complexity early, and it is by definition accidental complexity because you're not using it yet. What it ends up doing is making your code base much, much harder to understand. We have this attitude that when you add something to a project, that's when you start paying for that. And if you add something to your project and don't start using it for a time period, that an entire interim is really nothing but technical debt. Because it's something that's there and it's in your way, but it's not providing you any benefit. So this is the bad thing about buying industrial strength packaged software so that you can grow into it. All you're doing is buying a tremendous amount of technical debt that's just going to be in your way trying to use the bits that you already have. So those are all reasons that emergent design's hard. Let's talk about some things and some techniques that make it easier, some emergent design accelerators. And one of these, for me, big time, is the use of tests as a design tool. So normally the letters TDD stands for test-driven development. I believe it also stands for test-driven design, because design will emerge from tests. You'll get better abstractions, less accidental complexity, and a better atomic understanding of intent. But I wanted to be able to illustrate this to you guys. And so I did an example in my book, Productive Programming, that I'm going to recreate for you here. What I did was take a simple problem and wrote it two ways. I wrote it using just test after, which means write the algorithm and the right unit test for it, and then I derived a version using TDD. Let's look and see what's different between the two of them. And here's the problem I solved. This is actually an ancient Greek mathematician's observation about this weird little characteristic of numbers. He identified something that he calls a perfect number. And a perfect number is a number where you take the factors, which are the pairs that when multiplied together equal the number. If you add all the factors of a number up, it equals the number. 6 is a perfect number because its factors are 1, 2, and 3. If you add 1 plus 2 plus 3, it equals 6. 28 is also a perfect number if somebody wants to do the factors and figure that out. So is 496, and so is 8,128. I've done this talk a few times. There's also a 35 million number that I don't remember. So those are perfect numbers. So it's the sum of the factors of a number, not including the number itself. So I want to write some code to determine that. So here's some code in regular old school Java that does that. I have an isPerfect method. It goes and first gathers all the factors. It adds 1 in the number because those are always factors of the number. And then for 2 up to the number, if number modulus I, so that's the mod operator in Java, if the remainder of I going to number equals 0, then it's a factor, and I add it to my list of factors. I then sum them up and then decide if it's perfect by applying my formula. I write this code and I write tests for it, and everything looks good except that it's really slow. And I'm wondering if there's not some way to speed it up. And in fact, there is, with a little bit of observation around this part of the code. Because I can make the observation here that factors always come in pairs. So if my target number is 16, when I grab 2, I can also grab 8, because that's a symmetrical factor. So that means I don't have to loop through all the numbers to determine factors. I can short circuit that quite a bit. I could just loop as high as half the numbers and grab the symmetrical ones, but there's an even better one, which is what? Square root. Square root is by definition the number times itself, which equals my target number. So if I gather everything up to the square root and harvest their pair, then I've got a much more efficient algorithm, and so I change my code to do that. There, I'm just going up to the square root, and I'm harvesting both factors when I do that, but there's an edge case that breaks a test. It turns out that when you have whole number square roots, it ends up getting added twice. So 16 was my target number. When I add 4 here, I end up adding 4 again. That's easy enough to fix. I'll just add a little test condition there to guard against whole number square roots. And if it's not a whole number square root, then I'll add the symmetrical factor. And this now is fast enough, and this is suitable, so I now have my solution. The test-driven version consists of lots and lots and lots of little tiny methods, each one of them backed up by tests. You've already seen how the algorithm works, so I'm not going to go through these in any great detail. I will show you one really important one. But one of the points here is that TDD code bases tend to have a particular shape, in that they tend to have lots and lots of very small tested methods leading up to better tested methods, or bigger, coarser-grained methods in a pattern that Kent Beck called the composed method style of coding. One of the interesting side effects of this style of coding, and a question that I get asked frequently is, okay, we understand that testing is a good thing, so how much extra time do you budget into your project to do all this unit testing? Is it like 10% more time or 15% more time? We actually budget 0% extra time for doing TDD, because what we have found is you end up saving time because you spend less time debugging and chasing down weird breakages and other sorts of stuff. To think that it takes more time to do testing makes the mistaken correlation that developer typing speed matches productivity. And that's not true at all. In fact, sometimes that's negatively correlated, that somebody who's typing all the time is not doing much thinking or doing useful work. But now I want to look at a particular scenario in my little perfect number thing, and an observation that popped up in the TDD version, and that is, are the factors of a number a list of numbers? Turns out it's not. It's a set of numbers. And I realized that because I got a test breakage that says I was expecting 1, 2, 3, and 6, but I got 1, 6, 2, and 3. And it made me realize, oh, order doesn't matter in the factors. It's just a set of numbers, and the ordering is just a side effect. But now let's go back to my test after version. This little guard condition that I added right here, does that really have anything to do with whole number square roots? Turns out it doesn't. It turns out that the reason that's there is because I chose the wrong data structure to put my stuff in. And this happens all the time. You make a casual decision about something that doesn't seem to have any negative side effects, and then something like this, you start to optimize something, and a weird little breakage happens. Now, what you should do anytime you get a breakage like that is go back and reconsider every decision you've ever made all the way back to the beginning of time, but you never do that, especially if you can see an easy, quick Band-Aid to slap on it. So what I did was make my code more complex than it should have been by picking the wrong data structure, and the way that I fixed that accidental complexity was to add even more accidental complexity to it. Very often the solution to accidental complexity is more offsetting accidental complexity, not boiling it back to the original essential complexity. And that's why TDD is really nice, because it forces you to vet every little decision before it has a larger implication in your code base. You have to think about the building blocks before they go into the building that you're building out of those building blocks. Let me give you another example. So TDD, obviously very applicable to greenfield, brand new kinds of projects. But I'm talking about both kinds of projects here, so let's talk about an existing brownfield project in some lovely method like this. Now, this is from a little sample e-commerce site that I built, and what it does is not even all that important, but a couple of characteristics are. Now, I've actually tightened this code up some to make it fit on one slide, because it used to have blank lines. You know, every 3 or 4 lines of code would have a blank line. How many people do that inside your methods? You put blank lines to kind of delineate chunks of code that are having common behaviors. A few people are tentatively raising their hand. Everybody here does that. I know you do. I can tell by looking in your eyes that you do that. You know what that blank line of code inside that method is? It's a cry for help. Make me my own method. You've already separated out from everything else. All you haven't done is given it a name and tested it to make sure it works. That's what you're doing inside methods when you create blank lines, is you're separating it. Why not separate it and give it a name and a test like real code? And so I got rid of the blank lines here just to squeeze it all up, but you can make an observation when you're looking at code like this, that it kind of chunks together in reasonable kinds of chunks, 3 or 4 lines together, another 2 or 3 lines together. The problem is, I want to see if there's any interesting design stuff in this code, but I can't tell, because this is a big giant pile of code. It's really hard to distinguish the interesting things. I need to refactor this and organize it before I can tell if there's anything interesting going on in there. And so that's what I'm going to do. I want to take like the first 3 or 4 lines after try is really the plumbing of getting all the JDBC and transaction state and all that stuff wired together. So I'm just going to go in my IDE and scoop up all the lines that are kind of belong to one another and just extract those as methods and end up with this. Now, there's a side effect here of using a refactoring tool like this, because your refactoring IDE has a really strict contract that it promises it will maintain for you, which is, after I'm done, your code will act exactly the same way as it did before. I'm not going to make any important decisions for you like scoping or anything like that. And so the only choice when you have a bunch of local variables like this and you start scooping stuff up and refactoring them is your tool has to pass all these things as parameters. So you end up with tons and tons of parameters. But I'm an intelligent person. I know that I can take some of those and pull them out to the class level and be able to share them and get rid of some of these parameter passing. So I do a little more cleanup around that and end up with this version of the code. Now I can actually see what's going on. We set up some infrastructure, we add some orders and line items, we complete it. If something goes wrong, we roll it back, and finally we clean stuff up. The motivation for this style of refactoring comes from maybe a surprising place. This is what's referred to as the composed method pattern in Small Talk Best Practice Patterns by Kent Beck. The idea of composed method is that every public method reads like an outline of the things that it needs to do, and the outlines are private methods that make all those things come true. The really nice thing about this pattern is that you look at your public methods and it's a really nice summary of what's going on. And in modern IDEs, if you really care about that detail, you just hold down Control key and the method name becomes a hyperlink, and you literally just drill right into that method and see the details. But the details are not in your face all the time. They're organized so that you can actually see what's going on and make some decisions about things like design. Because I make the observation, once I've got this code reorganized, that, you know what, these 2 lines of code right here are the only things that are specific to this problem. I'm going to use the command design pattern and actually refactor this and build my own little persistence framework, or the beginnings of a little tiny persistence framework. In fact, those of you familiar with Spring will notice when I refactor this, it's very similar to the Spring do-in transaction command. Before I do that, though, I want to show you one more deeper example of refactoring toward design. Refactoring to harvest an idiomatic pattern. One of my contentions is that every piece of software has undiscovered little design elements lurking around inside it that you just haven't focused the right lens yet to be able to see them. So I need another metric. We have cyclomatic complexity, which is quite useful. Now I need another one. And this one is afferent coupling. For any kind of code artifact, whether it be class or package or namespace, the afferent coupling for that artifact is the number of references to that artifact, either by some sort of import mechanism or by direct, fully qualified name reference. And so in this case, the afferent coupling of this class is said to be 6. So in many ways, what afferent coupling allows you to do is go find the most important classes in your code base. So now we have 2 tools. We have cyclomatic complexity, which lets me go find the most complicated thing in my code base. Afferent coupling, which lets me go find the most important thing. Let's go find the most important complicated thing, because that's the thing I want to see. Now, I wanted to do this in a way that is reproducible. I did this as part of that the IBM article series, and I wanted people to reproduce this. So I wanted to pick an open source framework that anybody could play around with, that's been around for a while, that's quite mature to do this experiment on. And so I chose Struts. Struts is a very well-known framework, web framework in the Java world. Literally thousands of applications have been built on top of this. Major sites like delta.com are on Struts. It's in its 2nd major version. You would think that most of the design issues have been chased out of Struts over the decade and a half it's been around. Let's see. So I ran a little simple tool on it. This tool is called CKJM. It's a little tiny tool for doing Java code analysis. It gives me both cyclomatic complexity and afferent coupling. The CK there stands for Kittimer and Chimmerer. There's the Kittimer and Chimmerer object-oriented metric suite, and that's what the CKJM tool runs against you for you. And the way that, because this is a class-level metrics tool, the way it reports cyclomatic complexity is it gives it to you for the class. It's the sum of all the cyclomatic complexity of the methods in the class. So when we look at the Struts code base, for example, WMC is weighted method complexity. That's the sum of the cyclomatic complexity of all the methods in that class. And the champion in Struts looks like this class called double list UI bean, which has a 66. And just to give you an idea, industry standard says anything over 10 is kind of bad. I think that's way high. Anything over 5 gives me chills and nightmares at night. So 66 is really bad. And so this is the most complicated class in the entire Struts code base. And so I could leap into that with both feet and start trying to make the world a better place by refactoring that guy. But if you look across at its afferent coupling, it's only directly used by 3 other classes. So Herculean effort here may not give me a lot of ripple effect to other places. Let's sort these by importance instead. Turns out the most important class in Struts is component, which is not surprising, but that's not even what I'm interested in. I'm interested in high combinations of numbers. Remember, I'm hunting complicated, important things. And the one that leaps out at me in this code base is this UI bean guy with a 53 and a 22. So that encouraged me to go poke into this class and see exactly what's making that so complicated, and I found this guy. This is a method called evaluate params. My very favorite part of this method is the very last line of the method, which says evaluate extra params. So it's like the developer just got tired of typing at some point. It's like, oh God, okay, evaluate extra, okay, I'm done. So what this code does, this is a web-based framework. What it does is harvest parameters. So some parameters it harvests for you, some it does transformations on, and some it leaves alone. So that's to evaluate params and evaluate extra params. And I noticed that in a lot of the classes in the struts code base, the really complicated ones tend to have some combination of these methods, and so I did a little poking around. You can do this at command line, but your IDE will do this for you now. The command line invocation to do this, it says, give me all the Java source files, and then tell me within those which ones have some method named evaluate something params. And there they are. I have found an idiomatic pattern in struts. And I think this is a good example of this concept of an idiomatic pattern because back 15 years ago when they started working on struts, I'm sure nobody said, you know what, in 15 years the most complicated part of our code base is going to be how we handle URI parameters. That's such a simple thing, nobody ever thought about it, so they reproduced that code over and over and over and over and over again. Because nobody really looked at the code base through this lens of how much kind of egregious duplication is there. Now, I mentioned that I wrote this up as part of that article series, and there's a little epilogue to this story. Right after I published that version, one of the struts committers contacted me and said that he had independently discovered the same kind of little wart within the struts code base and had done what I consider is the right way to solve this problem, which is to extract it as an embedded framework. So if you look at struts now, there's a little parameter handling framework embedded inside struts. And by abstracting all that code out of the individual classes, he knocked off several thousand lines of code and several hundred cyclomatic complexity points off of struts and left the functionality the same. That's the kind of refactoring you'd like to be able to support, is get rid of a whole bunch of accidental complexity and just leave the essential complexity in place. So once you've identified these things, how do you capture them and take advantage of them? The first and easiest way is just harvest it as an API. You already call frameworks and APIs all the time, and so that's an easy way to do this. So I go back to this idiomatic unit of work pattern that I discovered out of my code base. The easy way to do this, of course, in a language like Java, particularly pre-Lambda Java, you use the command design pattern and abstract that away and pull that code into its own little thing. It's worth noting here that remember the entire page of code, the entire slide of code that I showed you before, that's what it eventually became. That's the things that are unique about that code and not generic. Part of the problem when you have this big piles of undifferentiated code, it's hard to see the generic code from the specific code. Once you get it organized, you can see that a lot more easily. The other way to capture these kinds of idiomatic patterns are with language features like annotations or attributes. They're called different things in different languages, but it's basically ways to attach meta information to things like methods. So in the Java world, for example, you can create annotations that stick to methods like this. So maybe for bizarre historical reasons, I can't let country names be more than 10 characters long. So I can attach an annotation on that and build an interface like that, and then build this very simple little validator class. All this does is loop through all the methods on a class, look for a particular annotation if it's present, and if it is, it calls this validate method. These are both abstract, so I subclass this guy, give it the annotation type, and tell it what I want to do, and it can do that. And so here's the max length validator that goes in and makes sure that none of the properties that I set have a length greater than 10 characters. These can be pretty sophisticated. Here's one that will go through and make sure that the country you've added to this region is unique, because these annotations can get access to underlying collections and other things that are present when it runs. So you can do some very powerful things with annotations and attributes. And here are a couple of unit tests that demonstrate putting those through their paces. The thing that's so nice about using annotations or attributes as a way to capture these kind of idiomatic patterns is that this is an orthogonal way your language has added expressiveness to your language, and it sticks out kind of like a sore thumb. And you really want those really precious things you've harvested to kind of stick out from other stuff. The other nice thing about annotations is it gives you really good locality to where you want to apply code and the thing it's being applied to by attaching an annotation to a particular chunk of code. The reason I bring this up, this is of course not applicable in every situation, but I notice a lot of framework authors using this language feature, but not a lot of people who are building software are using it, and I think that's too light a use of this particular feature because they add an entire new dimension of expressiveness to your underlying language. In fact, I want to take this even further and talk about the way annotations work in Ruby, which is an even more expressive language. So let's say that I wanted to limit testing in the Ruby language. And so let's say that complex calculation take a really long time. One of the distinctions you can make in the Ruby world is, am I running unit tests or acceptance tests? And so let's say that I've decided I only want to run that test during acceptance testing because it takes too long to run during unit testing. Ruby is very syntactically flexible, so it'll let you do something like this. Conditionally define that method. And say if the build environment variable is equal to acceptance, then define this method, and then of course it'll get run. But that's kind of cumbersome, and this is really ugly if I want to do this for multiple methods. I want to knock them out. And so the easier way to do that is just create an annotation, which looks like this in the Ruby world, acceptance only. The reason I did this little exercise is this is the entire implementation of acceptance only. This uses this mechanism called a hook method in Ruby, where I build a little function called acceptance only, and all that does, that means a private variable in the Ruby world. So that's going to be true or false depending on the state of that environment variable. This is the hook method. So every time you add a method to a class, after you've added that method, it fires the method added method for you. And method added says, remove this method unless that variable is true. So this is the computer science equivalent of the game whack-a-mole. You try to add it in, and this just sucks it right back out if that conditional is not true. And then it resets that flag to false again, so that you have to set that flag every time you want to suck one of these methods out. This is useful for a couple of other things in the Ruby language as well. Let's say that I wanted an approval class like this where everything that was declined was logged. Using method added, it's very easy to build this. What you do is go in and say, go and take that original method and give it a new name, then define a new method by this name, do all the stuff I want to do, and then at the very end, call the original method. Does anybody know what this is called in the .NET world or the Java world? This is aspect-oriented programming. This is, in fact, a before point cut in aspect-oriented programming. Does anybody know what this is called in the Ruby world? This is called monkey patching in the Ruby world. It's the exact same mechanism, slightly different level of gravitas about the name of this thing. It's called monkey patching because it was originally called guerrilla patching, like guerrilla warfare, and it was misheard as guerrilla, and so they thought it'd be funny to call it monkey patching, and that's exactly what that's called. So aspect-oriented programming and monkey patching are basically the same thing. The key difference, though, is that in Ruby, this is a language feature. This is not an extra thing that you've bolted onto the language to add this capability, so much so that the private, protected, and public words, modifiers in Ruby are not keywords, they're sticky annotations. So even language features like scoping is built on that, which means you could easily build your own unique scoping designation in the Ruby language if you wanted to, using this exact same mechanism. Very, very powerful to be able to get underneath like that. And similarly, this is an old example, but a good one. That's how you harvest things in struts, and that's how you harvest things in Ruby on Rails. Expressiveness matters in frameworks and in languages and in tools, and it matters a lot more than people give it credit for. Because I agree with Jack Rees, I believe that code is design, and if code is design, then you want the most expressive medium you can find. This is about doing pen and ink drawings versus watercolors versus doing oil paintings. The more expressive medium, the more powerful the medium, the easier it is to express your exact ideas. A lot of times this happens as a meta-language nature, so try to push for expressiveness. Now, I know most of you don't get to choose what language you use for your day job, but you can absolutely start pushing for expressiveness around the edges. So in your build tools, in your testing tools, one of the common pieces of advice I give people in the Java ecosystem is stop writing unit tests for Java code in Java. It's a giant waste of time. Write them in Groovy instead. It's a single jar file you add to your project. It never makes it into production. And the things that are hard in Java, like mocking and testing private methods, are trivially easy and built into Groovy. And it's a more powerful language in many ways. It has a meta-object protocol. It has a bunch of functional programming stuff built into it. Having those really sharp tools, even around things like testing and build, means that you spend more time working on real problems and less time worrying about plumbing and using blunt tools to beat against things. Another interesting aspect of this are abstraction styles. Most of us are very, very used to imperative programming, which encompasses structured and modular programming and also object-oriented programming. But there's more and more interest in functional programming. I talked about functional programming in my opening keynote this morning. These are just different shapes of tools. Just like there's a Phillips screwdriver and a flathead screwdriver and a hex screwdriver, different tools are meant for different purposes, and some problems are easier in some tools than others. And my point here is you don't have to completely switch language to sometimes shift the way you think about designing things. And a good example of this is anti-objects. This is from a paper that was delivered at UPSLA back in 2006, I'm wanting to say, called Collaborative Diffusion. And they make the observation that when you're in primarily object-oriented languages like a Java or a C#, that the metaphor of objects can go too far, making us try to create objects too much inspired by the real world. And anti-object is a kind of object that appears to do the opposite of what you think it should be doing and ultimately yields a simpler design. It's kind of like this. Is this a vase or is it two faces? The classic example of an anti-object design is Pac-Man. Now, I put this example very late in my talk because I'm about to explain to you how Pac-Man works. And after I do that, you are not going to be able to enjoy Pac-Man as much. Sometimes knowledge comes with a cost. So if you feel compelled to leave now, I will understand if you want to go play Pac-Man. This is a classic example of this anti-object approach to design because when you think back to the Pac-Man game back in the early 80s, 1980s, it had way less processing power and memory than the watch that I'm wearing right now. And they had a really hard problem to solve. How do we calculate the distance in a maze between two moving objects? And they didn't have anywhere nearly enough processing power to do that. So they built a really clever anti-object kind of algorithm. Now, if we were designing this today, we would build a ghost class, and we'd build a Pac-Man class, and we'd have several instances of ghost classes, we'd have methods to try to figure out how to calculate distance between them. That's not what they did. They built the whole thing as a state machine where every cell has rules that it runs every time through the game. And they invented this concept of Pac-Man smell, that when Pac-Man is sitting on a cell, it has maximum Pac-Man smell, and the cell he just vacated has maximum Pac-Man smell -1, and it decays really quickly. And now all the ghosts do is wander around semi-randomly until they encounter Pac-Man smell. They go to the adjacent cell where Pac-Man smells a little stronger, and they can travel a little faster than Pac-Man, and that's the whole game. They purposely threw you off here because they gave the ghost eyes, but the ghost can't see you. They can only smell you. So they should just be a giant nose. But that means that next time you play Pac-Man, you can run right up on a ghost because they can't see you coming. They can only chase you from behind. That's the only way they can detect you. So unless they just randomly turn into you, they can't see you. Even though they have big giant eyes, they're not really there. When Miss Pac-Man came out, they took the extra processing power to build a better randomizer, not to change the architecture of the game, because the game still works perfectly fine. We've actually applied this anti-object kind of approach. We were building this system that was handling leasing of train cars. And we were trying to write all these code to get train cars to organize themselves. And we realized this is a dumb idea. We need to model the tracks and let the tracks worry about where the cars go. And once we started thinking about it like that, it became much simpler. They have examples in the collaborative diffusion paper about modeling water droplets. Instead of trying to model the drop, they modeled the water that it falls into, and it turns out to be a simpler problem. So that's all stuff about finding and harvesting idiomatic patterns. Let me go back for just a minute and revisit last responsible moment. As I said, this is probably the trickiest thing in the agile software world, is how do you identify exactly when this last responsible moment is. Now, I'll give you some clues and an example of where a project that did it really well. If you think about your software stack as a collection of components, this can be components or services or libraries or whatever, and you look at each one of those in turn as to what level of complexity it's taking on over time. Occasionally you will see sharp upticks in the amount of complexity because that part of the system is doing more work, or we're having a lot of features in that part of the application at a particular time. That's a good time to look at that component and say, has your last responsible moment alive? Should I really be replacing you rather than spending a lot of time making changes to you? Another thing that's really common in the Agile world is this idea of spikes, which are time-box experimental coding exercises. This is the way you chase away unknown unknowns. Don't live with unknown unknowns. Do a really quick spike to see if you can figure out enough to make intelligent decisions about whatever this thing is. Spikes are never prototypes. This is code that never makes it onto your trunk of development. This is usually done at a dead-end branch because you're sprinting as fast as you can. You're not building properly tested, well-organized, pretty code. You're just trying to learn as much as you quickly can. You take the learnings and apply that to code in the trunk, but you never merge it directly into trunk like a prototype, because spikes are not prototypes. So let me give you a case study here of a project that I think did this last responsible moment thing really, really well, and it illustrates another point that I made earlier as well. This is a project that's still ongoing in Atlanta that I've worked on intermittently over the years. This project started in 2007 and is still going strong. This is OVE.com, onlinevehicleexchange.com. This is a site in the US that if you are a used car dealer, you can get a log on to this site and do online auctions with other used car dealers. So it's kind of the wholesale version of autotrader.com. This is a Ruby on Rails code base, and what's really interesting to us is the evolution of how asynchronous messaging made it into this code base. So very early on in the life of this code base, we had a request to be able to do asynchronous uploads. It turns out a really common usage of this site was for a used car dealer to come in and put in new cars in batches of 40 or 50 cars, and each car has lots and lots of pictures, because it turns out if you think that you don't trust used car dealers, other used car dealers really don't trust used car dealers. And so they want basically a picture of every molecule of the car they're about to buy online, sight unseen. And so every one of these cars has lots and lots of pictures, and it takes a long time to upload that stuff. And so the user of the application wanted some sense of progress. Give me a progress bar, or give me a landing page I can come back to see if it's finished or not. And so there was some speculation about how best to implement that, and an asynchronous message queue was suggested. But they also did a couple little spikes around some projects. And somebody on the project found this little thing, background RB, that sets up a little tiny single topic message queue backed by a relational database. And the tech lead said, you know what, that's good enough for right now. But this wasn't his first project. And so he was careful enough to put that behind the Ruby equivalent of an interface. And then we kept working. At about the 1 year mark, we got a second request for asynchronous behavior, which are timed events, kind of like cron behavior, run this at 2 a.m. every night, do these updates, et cetera. And again, we looked at the architectural implications, but we realized that, you know what, we can just spin up another instance of background RB, and it's good enough. At about the 2 year mark, we realized that we had a bunch of stuff that needed to run continuously, like updating caches and counts and things like that. At the same time, the DBAs had discovered that we were using a simple message queue backed by a database, and they started making this face at us when we saw them in the hallway, which we thought was probably a bad thing for intra-project relations. And so that was our impetus finally to switch to a proper messaging queue in the Ruby world, this thing called Starling, a very lightweight, small messaging queue that exists in the Ruby ecosystem. It took one pair of developers less than a week to swap out all the background RB stuff for Starling and had no impact on any other developer on the project while they did that. So let's see what happened there. So remember what I said before, that on projects, that at the very beginning of the project, the main characteristic is you don't know what you don't know. And so the knee-jerk reaction in many organizations is, well, let's just buy the fanciest one we can just in case, and we'll grow into that capability. But this is a terrible idea because you start paying technical debt for all those capabilities the day you add it to your code base and don't start reaping the benefits of those extra capabilities until you start using them. And if you've bought the most fanciest, best, specialist, most elaborate kind of framework in the world and you never end up using some of those features, you're basically paying money for technical debt that you never actually justify. But here I think is the more interesting thing for us. Notice that messaging infrastructure is traditionally an architectural component hard to change later. But the tech lead, when he noticed the fact that this is not when it's going to need to change, but at some point it's going to need to change, he was careful to wrap that around an interface so when it came time to change that, they could use the strangler pattern and change the implementation behind the interface without impacting anyone else. Basically, by isolating that behind an interface, he converted it from an architectural element into a design element, something that's hard to change later into something that's easier to change later. This is why you see so much thrust and emphasis in the agile architecture world around component and service-based architectures, because it has this characteristic that if you've got the isolation right, it makes the individual pieces easier to change because they are more components and less sticky architectural elements. So to summarize, evolutionary architecture and emergent design require good engineering practices. We have I'm sure you have this phenomenon here in the UK. When you go to an amusement park, there's a little cartoon guy that says you must be this tall to ride this ride. We have this in our microservices talk, that you must be this tall before you even start talking about that kind of architecture. And a lot of this tall means mature from an engineering standpoint in terms of DevOps and kind of the engineering parts of projects. If you're trying to deploy more than 3 services by hand, you've already lost. You need to have automated all that stuff before you even try to get into that. And this is the same is true here, that certainly things like refactoring is much easier if you have a safety net of unit tests that you can rely on. That shouldn't prevent you from trying to do some of this, but it certainly is easier the more kind of good practices you've been following all along. The negative side effect, very often, a big design up front and those style of methodologies is they tend to lead to over-engineering. This is a really terrible task that we put in front of enterprise architects to say, we have this gigantically complex software stack, and your job is to make sure it doesn't all fall down and go boom in 5 years, go. Well, the way that a lot of people react to that is just over-engineer the crap out of everything and hope for the best. But a lot of times that doesn't really help. Trying to predict the future a lot of times leads to over-engineering. This is a very subtle but important distinction. In the agile world, we're trying to prefer pro and reactive to predictive. In other words, rather than trying to predict the future, what we're trying to do is be proactive about enabling ourselves to change things in the future and being reactive to look at things that need to change to make sure that we can change them without a tremendous amount of pain. So the combination of pro and reactive, I think, works much better than predictive from an engineering standpoint. That's all I have. Does anybody have questions about any of this stuff? I've got a couple of minutes for questions if anybody wants to ask questions. I have a guy with a microphone wandering, so give him time to. It can be that I've stunned you all into silence. So you all agree 100% with everything I said. So that's good. We can all just, we got someone in front here. Go ahead. I'll just repeat your question.
Yeah, that's fine. So the question I wanted to ask you on the first one is related. There is a whole debate about functional versus object-oriented
approaches to design, and it seems like a wrong debate. It's different tools, and what I can see in purely functional code is the lack of design often, because maybe I'm missing something. But
You're missing something, big time. It's just a different design from what you're used to. So they don't design things the same way in the functional world than you do in the object-oriented world. You're used to seeing lots of classes and interactions and all these messaging and all that stuff, and none of that stuff's going to be there. It's going to use really small little functions and things like that. So let me give you an example of exactly what I'm talking about.
But what I see in functional code often, in purely functional code, which is not using classes, is a shared global state. Is a global state person? I mean, that's what.
I mean, you may be seeing that, but you're looking at bad functional code. So you
Exactly.
stop looking at that code. So that's the shared functional state is not shared state is frowned upon almost universally in the functional programming world. So you try to minimize that as much as possible. You do find naive developers, you know, every developer, when they move to a new paradigm, they do bad old paradigm code in the new paradigm until they learn to use the new one. So I think that's probably what you're seeing manifest. But
So
let me give you an example of exactly what you're talking about. So you're used to in the object-oriented world to create something like a framework that does database connection pooling, for example. And you're used to creating a class that has 4 or 5 parameters, and now it handles database connection pooling for you. You're seeing that as a class. In the functional programming world, so for example, in a Scala or Clojure, the way that you might model that is instead of building a class that's holding on to that state, build every one of your database functions that takes 4 additional parameters up front, which is like, you know, URI and username, password, whatever stuff you need to pass into it. Then, before you start using those in your project, using currying to automatically supply the first 4 parameters, yielding you a function that just takes 2 parameters, which is SQL and parameters. Now you've supplied that state to that function, but that state is being maintained by the language now. And you don't have to worry about maintaining that state in that separate class and all that stuff. So the same kind of mechanism is there. We're passing that stuff invisibly, so you don't have to see it every day. You've just done it in a different design style. So that's the completely different way of thinking about even mundane things like passing parameters, holding on to state, or things like that. So I think if you look at really good code in like the Scala world, Akka's really good, high quality Scala code. Play, the second version of Play has some nice stuff in it. Anything in the Clojure space, in the open source Clojure space, you're not going to see any shared mutable state anywhere. They do take a lot of care about that. But it is, you're right, it is a very different way of thinking about things. And we've got to get away from this idea that there's a one true programming language that will solve all of our problems elegantly. Because it's just not true. Our problems are all in different shapes. We need to get more polyglot in our world and start using right-sized languages for the kinds of problems that we're solving. I think the experiment from the last decade proves that as much as you try, you cannot get a single language to solve every problem. And you're actually better off picking different languages on the same platform and mix and match them. So I think that's where we're going. In fact, I don't think any of the ThoughtWorks projects for ThoughtWorks Studios are not multi-language now. They're all polyglot in one way or another. Okay, a couple of questions. Whoever can get there first.
Hi. You mentioned about technical debt and adding features that builds technical debt. Now, there's been a few talks this week about feature toggling. Mm-hmm. Do you think feature toggling is a technical debt?
Yes, it's purposeful technical debt. It's exactly what it is. Yeah, okay. It's on purpose. You're purposefully adding technical debt to your code base to support other engineering practices you want to support. So the poison in feature toggles is adding them and then never taking them out. That's the worst possible thing you can do because now you create permanent technical debt. So in mature feature toggles, as soon as it's resolved, I want it in there or not, you go and strip all the toggle code out and just leave what's supposed to be there. Okay, it is absolute purposeful technical debt to support other engineering practices. No doubt about it. Yep. Behind you, on both sides.
I've been on a few projects recently where the pendulum's gone totally the other way. And they say, oh, we don't need any architecture or design. Mm-hmm. Often using your emergent design as justification or a very bad interpretation of emergent design.
Yep. They're trying emergent architecture.
Yeah. So I want to ask you, how do you, when there's unknown unknowns, and one of the last things you said was, emergent design is great if you've got your first partitions correct. How can you do enough architecture to get the partitions correct without going overboard?
Well, it's got to start as simple as you possibly can. So, I mean, there's some basic characteristics you're probably going to know. You're probably going to know what kind of persistence is going to be shoved down your throat, because you probably won't have a choice of that, or the problem is going to dictate the choices around that. You're probably going to know what your company's deployment stack is. So that's going to put constraints around the kind of choices you can make there. So, I mean, there's a whole set of existing constraints that you have to make these architectural decisions within anyway. Within those constraints, you need to find a way, okay, what's the simplest thing we can start with and validate and get so we can start iterating over the top of it. So maybe you're a purely .NET shop and you decide, you know, our constraint is SQL Server and C#, but maybe let's start building a service architecture, you know, the smallest little services we can in C# and start iterating on like that, on top of it like that. I think it's a mistake to think you could do emergent architecture. You know, so one of the points I made in my keynote today is that meta work is more interesting than work. That's exactly what you see manifest there is, you know, doing architecture and kind of diligence is kind of boring. It's way easier to just start hacking on stuff and get it together, but that's probably not prudent. So you need to find a pragmatic mix there of enough stuff to get going so that we have a foundation to build other stuff on, but not sit for 2 years and design a cathedral that's not going to be that useful. So there's a definite tension between there. But as you're saying, there's no way we're advocating don't do architecture. You have to have architecture because that's what everything sits on. So that's a misinterpretation for sure. Yep, back in the back.
Any tips about getting the stakeholder to buy into that technical debt and you know, complexity and that refactoring? Because one of the things that I'm finding, or we are finding, is yes, we can build and we can do whatever we want, but our stakeholders are not necessarily interested into, or are interested into how complex the code is, how much, you know, it's going to cost them over X number of, you know, X period.
Yep. So one of the things you have to have a really good feedback loop between the developers and the subject matter experts. I think Alan made a point in his keynote this morning that a lot of times people ask for things. It's like, oh yeah, I can give you that in 2 hours, and they'll ask for something that sounds a similar size problem to them, and it's 15 research assistants, you know, and 8 years of research and development. So it's really important to, and this is why it's really important to have developer types within like planning meetings for features, because your business analysts are going to come up with things that sound really cool and they don't realize how really cumbersome those are. If you let those get embedded in concrete in requirements documents somewhere, and now all of a sudden you've got this horrible thing you have to deal with, whereas if you're there in person say, well, you know, that's really hard to do, but you know, this other thing's pretty easy to do, and that gives you 80% of what you're after there. Is that enough of what you want? And have that kind of iterative discussion about things. That's really useful because it gets it also into your end users' minds that there's a cost associated with each of these things. A lot of times, if they're divorced from that process, they don't really think about the cost and relative cost. So there are all these games that they play in the Agile world, you know, a virtual $100 you can spend on things, and you have to, you know, this feature costs 20 of the virtual dollars, and this one's 3 of the virtual dollars. So, but that's really just a way of get in their head, you know, the relative cost of things. The other thing I would say, if you're trying to convince somebody of technical debt, demonstration trumps discussion. You've got to find some way to illustrate that technical debt in a way that makes it stick out, and a way to start tracking it so that when it starts coming down, you can track that too, because that's the other thing you need anytime you introduce some sort of practice like this, is being able to demonstrate that it's needed and continue to demonstrate that it's doing a beneficial thing. And you'll get a long life for something if you can show that it's actually continuing to work. Particularly if you're not much of a metrics-driven organization now, that will open a lot of people's eyes that, wow, you can actually track interesting things on projects and maybe encourage people to track some other stuff. Probably time for one more question, so he's running over to you now.
Yeah, I was just wondering if you could maybe elaborate on your last point in the presentation about the difference between predictive and proactive. I can't remember what it was the previous slide.
Pro and reactive over predictive.
Yeah, because I mean, the example that you gave of the progress bar thing, that the guy who's doing that knew to put that behind an interface, and that kind of seems like a thing that you'd need to know that you would need to change this in advance, and I don't know how you'd distinguish between those. So
that's certainly something that comes from being experienced on projects and realizing that something's probably going to need to change. But in general, when you start working on real service and component-based systems, you start looking for those natural boundaries around things, like transactional boundaries or domain boundaries or any kind of technical boundary like that. That's a really easy thing to kind of carve off. So I don't think it was any particular amount of genius or prescience that he had. It was just, you know, enough experience saying, oh yeah, you know, that's we've got this really simple thing in place, and it's probably going to get creaky at some point. We should probably replace that later. I mean, there is certainly a little bit of design up front when you're thinking about that, so you don't want to get too far into that, but at the same token, you don't want to just blindly stumble into stuff. I mean, if I know I've got a site that needs to scale to hundreds of users, I'm not going to start with, Node and some crazy thing and say, oh, we'll just refactor it architecturally, to get the scalability we need in the end. That's probably not going to work, so you have to, there's some balance in there, and that's really the tricky part. Architecture and software is just tricky full stop, and the tricky things in the Agile world are getting those kinds of, how much design, how much architecture, that tension just right. Just like tricky things in the big design up front world is, exactly how low a level do you go before you start coding stuff. So different tensions, different trade-offs. All right, well, looks like I'm just about out of time. Thanks very much for coming. Hope you enjoyed it. Hard to change later, and that determines if it's an architectural element or a design element. So for example, the database you use is architectural because you can't easily change that out. The web framework you use is architectural because you can't easily change it out. But the way you use that web framework, the way you use its validation bits and how you use its workflow, those are all aspects of design, which are things that are relatively easy to change later. And this very abstract blocks diagram is trying to capture the sort of essence of this in that these gray boxes at the bottom represent architecture. And you can't have software without architecture. There's no such thing as emergent architecture because the architecture is the thing everything else rests upon. That's why I make this distinction between evolutionary architecture and emergent design. Because the cost of change is less expensive for design elements, you can afford to let those emerge over time. But for the architectural elements, something has to be in place. And so part of our effort there is to make it so you can evolve those architectural elements slowly over time and make as many things as you can cheaper to change by making them design elements. Because the other half of this definition is you really want as few architectural elements as you can get away with. Because while architectural elements provide scaffolding and code you don't have to write, it also represents constraints that you're introducing. And what you want in the perfect world is all the capabilities and none of the constraints, and you try to optimize toward that. Most of this talk, I'm going to focus on the top part of this, the red boxes here, around design, and in particular, this idea of emergent design. So I should give a definition. The Webster Dictionary says that something that is emergent if it rises out of something that covers or conceals it or comes to light. And a second definition says something suddenly arising or suddenly appearing, arising unexpectedly, and calling for prompt action. These two definitions loosely correlate to the two different aspects of emergent design I want to talk about. And here's the first one. Let's say that conceptually you have a problem that's like this. It's kind of a tangled mess, and there's relationship things between things, but you can't quite discern what that relationship is. And you think about this while you're at work, you think about it while you're riding the tube on the way home, and you think about it when you're mowing your yard, and when your spouse is talking to you and you're supposed to be paying attention to them, there's still a background thread that's kind of thinking about this problem at work and trying to figure it out until you finally think about it enough until it resolves itself in some sort of reasonable, meaningful structure. That's this exercise of finding abstractions and patterns that already exist in your code. You just need the ability to go find them and harvest them out of your code. So this is very much an existing project kind of emergent design technique, or a brownfield project kind of technique where you're looking for things in existing code. And I'll show you using some metrics and other things in just a minute of some techniques where you can go find hidden little designs. Traditional engineering has spent a few thousand years working on mathematical techniques that give them predictability, so they don't have to build bridges to test them to see if they're going to stand up or not. And for quite a long time, big companies like IBM tried to do the same thing for software. Back in the 60s and 70s, IBM got disgusted at how wishy-washy this whole software engineering thing was, and they sent Fred Brooks and Barry Boehm off and said, make this a real engineering discipline. And mostly what those two guys did when they got finished was write books about how this is never going to be a real engineering discipline. That's where Mythical Man Month and all that research comes from IBM. But it turns out that this is probably chasing something we don't need. Because the reason they have all this predictability in engineering is because it's so expensive to build stuff. But our manufacturing is essentially free. I mean, every time we stop typing, we get stuff manufactured, and so we can easily manufacture things in realistic kind of environments and test the real thing and not the predicted behavior of the real thing. So for us, we get engineering rigor in testing. Believe me, architects would love to be able to take a small subsection of a building and see what kind of stress it reacts under in a realistic way. And while they have some tools to do that, it's still predictive around math. It's not the actual thing. And I also think that if architects could actually do test-driven development, we would have the most elaborate Jetsons-like buildings you've ever seen in your entire life. Testing is the thing that gives us confidence that even though we have this pile of disparate parts, we can separate each one from the pile and completely understand its characteristics before it goes back into the pile and contributes to the larger piece of our software. And so Jack Rees concludes his essay by saying software may be cheap to build, but it is incredibly expensive to design. Because basically, everything that you do in software that might change the source code is part of the design process. So that means that testing is part of design, QA is part of design, operations is part of design, because if your operations group comes back and says you can't use this piece of library from the internet because of security concern, that's changing your source code, that's part of design. And this is a really, really expensive thing. And so part of the idea in emergent design is let's try not to waste a lot of this really, really expensive design time. So I talked about this distinction between architecture and design. There was an essay that Martin Fowler wrote a few years ago, probably 5 or 6 years ago, called Who Needs an Architect? It's still on his website. And he's talking about the role of architects in agile projects. And he sort of accidentally gives what is still my favorite definition of the architectural elements in software, where he says that the architectural elements in software are the things that are going to be hard to change later. And so for any piece of your software stack, you can kind of ask it, are you going to be, was not particularly to make safer bridges at first, it was a cost-saving measure, because it's simply too expensive to build prototype bridges and roll heavy stuff over them to see if they collapse or not. So they needed to invent all this predictive kind of math because it's really expensive. But software is not expensive at all. In fact, every time you stop typing, an army of gnomes inside your computer springs to life and manufactures your design on the fly for you. You don't even think about that happening anymore because compilation is just this magical background process that just happens. And so Jack Rees says, given that software designs are relatively easy to turn out and essentially free to build, an unsurprising revelation is that software designs tend to be incredibly large and complex. The last part of that quote got cut off, but the last part of it is that they tend to be incredibly large and complex. We just think that we're bad at software design. It turns out it's a fundamentally hard problem to solve. It's one of the hardest problems that we try to solve from an engineering standpoint. And here are a couple of reasons why. Here is a US-based plug, but just imagine if this were a much larger UK-based plug. And imagine it were part of this hotel in the wall over here. And you'll notice over here that the case doesn't quite cover the hole in the wall. A similarly small error in a piece of software will cause that software to crash and fail, but that small problem will not cause this building to collapse if that happens to be the case. So the tolerances in software are impossibly fine compared to the real world. One small thing will make your software stop functioning. Now, it's easy to spackle in that hole and just remanufacture the whole software stack, but the tolerances are really, really fine. We also don't have locality of fault to origin of fault. We may have a condition that sets up an instability that doesn't manifest for 100,000 lines of code away. If you're an airplane forensic engineer and the wing falls off an airplane, your first place is probably go check where the wing is connected to the airplane, because there's a locality of fault to the cause of the fault, which we frequently don't have in software. We also don't have the same kind of economy of scale. The Golden Gate Bridge in San Francisco has more than 1 million rivets in it, and you can bet that the people who understand the structural characteristics of bridges can tell you what contribution those million rivets make to the overall structural integrity of the Golden Gate Bridge. We build things that consist of lots and lots of parts too, but every one of our parts are handcrafted. This is back like when blacksmith used to make nails. You know, that was the blacksmith's #1 job, not making horseshoes, but making nails, because people needed nails to build houses, and each one of them was unique because they were handcrafted nails. That's exactly how we build our tools and software now. All of them are handcrafted. It has defied our ability to create reasonable components in software, although we keep trying. We're at the wrong level of granularity. So this talk is, as you probably guessed, about emergent design, and this is a part of the really interesting piece of the kind of agile architecture world, because this is about architecture and design. I've actually written quite a lot about this subject, and there is an article series out there on IBM Developer Works. There are 19 installments in this series on evolutionary architecture and emergent design, and I'll explain where that name comes from in just a second. That's a hideous, awful URL, so you don't want to use that. This is a much friendlier, modernized, shortened version of that, but this has a link to Developer Works and has some of the stuff I'm talking about here and lots more stuff out there as well. What I'm going to be talking about in this particular talk, my agenda, is to poke around a little bit and investigate what we mean when we say software design. And I want to tease apart the distinction between architecture and design, because if you can separate those things, you can build separate techniques around each one of them. I'm going to talk about things that make emergent design difficult. Then I'm going to talk about some things that make it easier and enable it. And then finally, I want to talk about some concrete techniques for once you've discovered these little patterns lurking in your code to help you find those things and then harvest them and take advantage of them. But I'm going to start with the poetry of Donald Rumsfeld, who very famously said, "There are known unknowns." That is to say, there are things that we now know we don't know, but there are also unknown unknowns. There are things we do not know that we don't know. And he didn't realize it at the time, but he was really talking about software when he said this, because this, it turns out, is the killer characteristic of software. It's the unknown unknowns. Because you go into projects with some known unknowns. We need to add geocoding to this application, and I'm not quite sure I can spell geocoding, but you know that you need to reserve a chunk of time to investigate and learn how to do geocoding. You can anticipate that as the unknown unknowns that is the killers. And that's the real nail in the coffin to all the big design upfront kind of techniques and softwares. They all suffer from the unknown unknowns and end up nabbing them in the end. So there's a lot of effort in the agile architecture world to try to stop reacting to things that we don't know and instead build emergent and evolutionary style architectures and designs. Because we realize at some point the future is really, really hard to predict. And instead of trying to build a better and better crystal ball, why don't we step back from that and make the future when it comes not quite so scary? So one of the questions that I want to answer, or at least start to answer in this talk, is this one. What do we mean when we say software design? And fortunately, someone has already answered this question for us. In an essay written in the fall of 1992 in the C++ journal, Jack Rees wrote this very famous essay called "What is Software Design?" It's still available there, and it's still well worth reading because you would think that it was written yesterday. And one of the interesting things Jack Reeves does is try to do a deep metaphorical comparison between traditional engineering and software engineering, as opposed to the very shallow metaphorical comparison that we use when we describe what we do to our parents or our grandparents. Yeah, software development's like bridge building. No, it's like gardening. No, it's like mountain climbing. These are all very shallow metaphors. He tried to do a deep metaphorical comparison between traditional engineering and software engineering and reach some interesting conclusions. One of which is the final goal of engineering activity is some type of documentation. If you're a civil engineer and you're tasked with designing a new bridge, what is your output for that task? Is it a new bridge somewhere? No, it's a plan for a new bridge with very specific environmental constraints in place and with the due diligence in place to understand what stresses and other sorts of characteristics need to go into that bridge. When the design effort is complete, that design document is turned over to a manufacturing team, which is a bunch of guys who know how to take architectural plans for bridges and actually pour concrete and rebar and make it into a real bridge. But now we get to places where there's a deep difference between traditional engineering and software engineering, because manufacturing for physical things means stamping out atoms into new shapes. And it turns out it's hard to refactor atoms. Once you've got them stamped in a particular shape, doing something beyond just melting them down and restamping them is very difficult. And so in the traditional design world, when you had hard constraints over the things you produced, there was a lot of need to do a lot of design up front because the manufacturing process was very error-prone and had to be very precise. But we don't deal with atoms in our world. We deal with bits, and bits are very, very soft. In fact, it's called software for a reason. So what is the manufacturing process for us? What is the thing that takes a design and converts it into something that manifests in the real world? It's compilation and deployment. That's our manufacturing process. What that suggests is that in our world, our design document, our blueprint from an engineering standpoint is the source code. And not just some of it, the complete source code. Because any change you make to this document changes what gets manufactured. So even if a QA person suggests a bug, that bug means you change something in the source code which changes the thing that gets manufactured. But here's another big difference between traditional engineering and software engineering, is that traditional manufacturing is expensive. Stamping out atoms is expensive. The reason that they developed all these techniques for civil engineering